webinar on Neuromorphic Computing hosted by IEEE Robotics and Automation Society. Thank you all for joining us. And I'm very honored and privileged to welcome our speaker of the day, Mr. Utkarsh Singh. He is the editor of IEEE India Council newsletter and senior hardware engineer at Samsung Electronics. Thank you so much, sir, for joining us. For the welcome note, I would like to invite Anupama Monsi Thomas, Joint Secretary, IEEE SPSJCET.
Good evening, everyone. Hope you all are safe and sound, and thank you all for showing up this Sunday evening. I'm Anupama Monsi, Joint Secretary of IEEE SPSJCT, and I feel privileged and happy to have you all here for today's webinar on the topic Neuromorphic Computing, conducted by IEEE RAS SJCT, IEEE SPSJCT. I would like to thank Dr. Arun P., branch counselor of our SP, for his support of the event. Now, over to my duty. Our speaker for the day is Mr. Utkarsh Singh. He is the editor of IEEE India Council newsletter and senior hardware engineer at Samsung Electronics. I'm indeed privileged to have this opportunity, and I heartily welcome you, sir, to enlighten our students with your words of wisdom. Over to you, sir.
Hello. Am I audible?
Yes, sir.
Yeah, thank you so much, Anupama. Thank you, Raina, for welcoming me here. Firstly, I would like to tell everyone that this will be a very informal session. So there should not be any gap between the speakers and the listener. So if you have any doubt or if you feel maybe you need any clarification at any point, just let me know. So neuromorphic as a whole is a very broad spectrum field, and it's a very, I wouldn't say it's a very new field, but it's somewhat has taken up pace in the recent years. So I will not be able to cover all the aspects of it, but I will try my best to give you as broad perspective of neuromorphic as possible. So I would like this to be a bit interactive as well. So I'd say you guys can message in the chat, or maybe Raina can tell me like which year people are here, undergrads. I hope there are undergrads. So which
Yes, sir.
Like majorly
Yes,
they're here. So like first year, second year, third year, fourth years.
Sir, mostly first years and second years.
Okay, perfect. So, okay. So that makes sense because the way I've put down the whole PPT, the whole flow is to give you a general idea as to what this big buzzword is and what all does it encompass. So if I can share my screen, just let me know when it's visible. Yeah, can you guys see my screen?
Yes, sir.
And the PPT as well, right?
Yes, sir. Yes.
Oh, thank you. Okay, so this is going to be a beginner's guide, just a bird's eye view to what neuromorphic computing is all about. You guys would have probably guessed, neuro means something that is to do with the brain, and morph means, to just like copy it or, take from it. So it's like, in simple words, it's basically brain-like computing that we have. Now, I'm going to try, like, your first question would be, but why do we need it? I'm not gonna answer what is it. I'm gonna answer that later. I'm just gonna tell you like why do you exactly need it? What is the need? Because we have so many forms of computing that we already have. Why exactly? What is the point of this? What is the purpose of this? What is the motivation behind it? So, starting out, we all want faster computers and phones. Like, there's no limit to it. We can give we can get as many fast phones as possible, as many fast computers as possible, but we still have this hunger for more. So to get way faster computer, and I'm not talking about processing speeds like 2 times, 3 times of current speeds. I'm talking about 10 times, maybe 100 times as well. So in your current computers and phones, that is the scale that we talk about when we are discussing neuromorphic computing. Now we want these better voice recognition system. We want more secure systems, and futuristic technologies that we've always like dreamt about, read in comic books, seen in movies, like robotics, self-driving cars, IoT, which is essentially your robotics and automation society would discuss these topics, right? Robotics, self-driving cars, IoTs. But you guys must have heard that there are a lot of challenges that these technologies face, right? Like 10 years back, we used to see these movies, Iron Man and other Marvel movies, DC movies, where we saw these like robots, different kind of technologies that are there. But we have not quite gotten there yet. Yeah, as a kid, even I used to dream, we'll have it in 10 years later. But we do have these technologies, but they're at a very nascent stage. So what is stopping them from, blowing up and becoming a part of a reality? And neuromorphic computing is one of those things that aims to bring in this era of these new technologies. Now, one more thing that I'd like to tell you guys about is one major challenge in robotics or in such systems is that they are very power hungry systems, and there has to be a way to reduce this power. Again, neuromorphic computing helps solve these challenges. Self-driving cars require very fast systems. There should not be any delay while the information comes into the through the camera of the car, and then it is processed, and then a decision is made. They want very fast devices, and again, neuromorphic computing aims to solve that aspect as well. So this time and energy that we're dealing with is a very big challenge of modern computing. Now, if I have to like shorten it down to one thing, neuromorphic computing aims at providing a better AI experience, a better artificial intelligence or machine learning, as you might want to say it. But the fact you might be thinking is, okay, we already have artificial intelligence. Why exactly neuromorphic computing, right? So here's the thing: artificial intelligence and all these algorithms and softwares that you guys build are have a limit. Now you might feel, how do they exactly have a limit? We can always make better softwares. We can always write better algorithms. But in the next few slides, I'll tell you what that limit is and how this neuromorphic computing aims at overcoming that limit and making your AI experience, making your algorithms even better, even time and energy efficient. So again, the question, but how are we able? Will we be able to do that? Now, because I've said a lot of buzzwords like robotics, artificial intelligence. I would like try to sell you guys that this is gonna solve it, but the question remains how. And if I don't provide these facts, you might not be satisfied in this with this session. So answering the question, first we need to dig deep, like where exactly the problem lies that we're trying to solve. That limit of computing, whether it is big data, data science, artificial intelligence, where is the root cause? Where is the essential problem that we're trying to solve? So the problem is actually with the way we use modern electronics. Now, with this statement, you might be thinking this does not make any sense because modern electronics is so good. We have smaller and smaller systems that goes scales smaller every day. We're getting slimmer and smaller phones. We're getting more features. We're getting more processing. What is exact issue with the modern electronics that I am trying to say here? So here's the real issue. If you go deep inside a computer, and electronic students or computer engineering students might be familiar with this, but I'll repeat for you guys. So whenever you take any processing system, be it your phone processor, be it your Intel processors, be it your Qualcomm Snapdragon processors, you have two essential units. One is your processing unit that you guys call it as a CPU, and one is your memory where everything is stored. Now, a CPU always has to access the memory, and then it has to take stuff from the memory, it has to process it, and it has to send it back to the memory. Even any input you give on your keyboard is sent to the CPU, and related items are taken from the memory, then the processing happens, and then they're stored in the memory. Now, there is a bottleneck if you consider it. Like, processors are essentially very fast, but memories are comparatively slower because they have to write, they have to read stuff, so they're not that fast, and they're not that energy efficient either, the current memory designs that are there. So there is always this bottleneck. Like, no matter how fast a processor you make, if the memory is not that fast, your system is going to have a bottleneck and it's not going to perform to the limit. And this issue, even if we increase the memory, like read and write speeds, still there is this issue where you will face this bottleneck at a certain point. A limit actually exists where this issue is seen. And that actually brings a lot of problems. Now, why does it bring a lot of problems? For your day-to-day computational task, it's not going to be a problem. But when you run algorithms of, machine learning, artificial intelligence, or big data, uh, this interaction happens a lot. And it let you guys get in your minds like what the number should be. Like, if I say, like, out of what percentage of time and energy is used in transferring this data from the memory to CPU and other places, from the total processing time that or energy that it takes. And I've received answers that were like 20%, 50%, 60%. It's actually more than 90 or 95%. So 90 to 95% of your training algorithms or your big data softwares actually use to transfer stuff here and there from CPU to memory, here from this part of the processing unit to that part, over 19 to 95% of the time and energy. Now, you understand where the problem is, right? Here we have a bottleneck, and these kind of algorithms always in present hardware architecture always use these kind of paths, this interchange. And this is the issue that we're trying to solve, that traditional digital computing systems have this issue, that you need to fetch from the memory, you need to store it, you need to transfer the data here and there. And 90 to 95% happens through this. And if this is slow, this is going to be a big problem. That is why we don't usually prefer to run modern AI algorithms on CPUs. We use something known as a GPU for that. And I'll come back to that in some time. So I hope you guys understand the problem at hand here. Our processing and our memory is happening in different places. So when neuromorphic computing was proposed, it was way back in 1980s. And the person who proposed it, what he said was, why not use analog systems altogether? Why not try to mimic the processing of the brain in analog systems? Because analog systems don't have this memory or compute kind of thing. So initially that idea started out like that, but now it has grown into different other fields. Even digital systems can be neuromorphic if you build them the right way. So what is the commonly used solution? As I mentioned before, what we do is we do most of these things in something known as a GPU. You would have heard NVIDIA GPUs, AMD GPUs. So every company is now making their own GPU. And GPU, what they essentially do is they split these processing cores into smaller cores, and they split smaller memories in them. So they try to bring them together. And because of that, they are able to do these operations much faster. But even despite that fact, we require a lot of time to train these systems, a lot of time to actually get our algorithms to run, even on these GPUs. And it's still a big challenge because they use chunks and chunks of energies. So whenever you use your phone, like I have this phone here, so you call OK Google, you call Hey Siri, whatever you do, your voice, whatever your voice instruction is captured, like I want to text this person, hi. So that is captured, that is sent out to these big servers at Google or Apple, and there the processing actually happens. And the final output is relayed back to your phone. And, wouldn't it be so neat that if I could have everything happening in my phone itself? But with the modern technology, it is not possible because the huge energies that these guys take, your phone will start to heat up. And, there are smarter phones every day, but essentially this is not a reliable solution, a feasible solution to have on your phones, because that is where the limit is. That is why almost all these voice recognition, AI related things usually happen on the cloud, and then final decision is relayed back to your phone. That is why you cannot use any of these voice recognition features, or most of these voice recognition features, on your phone or on your laptops. So here the solution, so neuromorphic computing essentially says is what we're trying to do is we'll take processing, we'll take memory, and we'll try to bring them as close as possible so that that interchange takes less of time and less of energy. And GPUs are one way to do that, but as people are starting to use more and more of these applications, GPUs are not really the best solution, at least in the current form. So modern solutions, which a lot of companies have brought out, is what they do is rather than having many cores, they have many cores of these. They try to implement these neural network structures right on the hardware, and then they make these many cores. Like this is one of the chip by IBM, and what they've essentially done is this: they've had this compute, like processing and memory. Then they have another core which has processing and memory. So they've essentially brought it down closer, and they have done what happens in the GPU. They've made a lot of cores out of them, and then this is said to increase, and this does increase the efficiency of, the energy efficiency, and this does reduce the time. But so this is one way how, neuromorphic computing can be done using digital systems. They're working, many companies like Intel, IBM, Google are working at the architecture level. So they're trying to bring memory and computing close. But even if you think about it, your memory and computing are still separate. They're not actually linked, right? So it's one aspect of neuromorphic computing that is being followed, and at the industry level. And people are always looking out for better ways to overcome these challenges. Now, this is one of the chip, and these are some of the major projects that I'd like to show. Intel. So you just mention the brand name, and like neuromorphic processor, search with it. So you will find these different products. And you must have heard Apple in its chip is including neural engines, because these AI related tasks are becoming so and so extensively used around the world that companies have to include a separate processing engine which has memory and processing closer to each other to accomplish these tasks right on the phone itself. But it's still not at that level of maturity, because as we see in digital systems, you always have memory and processing happening separately. So, like, what would the future look like? What would it be like, right? That is the major question. So essentially, there are now multiple groups of people doing multiple things. So what some people are doing is, as you see, the companies, now there are some people who are working on algorithms and software. These are majorly the computer science people who are making newer algorithms that, maybe use less number of weights, less number of training samples to give a higher percentage. But the new trend that is ushered into each kind of industry is making these new kinds of architectures that I just showed in the previous slides to actually be able to tell, like, what to actually be able to reduce this bottleneck. So we're trying to, so what some companies are doing is they're making a whole new processor at the location of the memory itself, so that this interchange reduces. And essentially that was not the initial goal of neuromorphic computing. It was wanted to do something else that I'll just discuss. But since we have digital systems where memory and processor has to be separate, these companies are trying to bring in these kind of new architectures that I just showed, like these kind of architectures, to effectively and efficiently try to reduce time and energy. So that your phone does not start heating or melting if something like this is run on it. That is why majority of the GPU systems you see have fans or cooling systems, because essentially because of this interchange, there is so much heat that is generated that, and to run certain state of the art neural networks, to train them, it actually takes around like hours to train them. And that is something that we don't want. That is something we're trying to resolve using this so-called neuromorphic computing. So essentially, neuromorphic computing is basically AI ML algorithms that you're trying to implement on a chip. And why on a chip? Because so that you can train your system faster. It takes less time, it takes less energy. If it takes less energy, you can have it on your phones, you can have it on your laptop. You might not even need internet connectivity. Or IoT systems, so you can have sensors detect then and there only what action needs to be made. So if a fire has just broken out, a sensor will not need to relay the information to the processor and then take it back. It can just process on the location, and it can actually drive the water systems to prevent that fire. So all these futuristic applications that you see will only be possible if we are able to reduce this bottleneck. Or maybe, like, I don't think so this will be ever gone, but reduce this bottleneck. But there is a certain class of people who are working on the circuit and the device level aspect, which I just want to talk briefly about because it has not reached the industry yet. But a lot of companies are pumping in a lot of money to, get new kind of devices and get new kind of circuits in order to, bring in better processors, bring in better systems, maybe 5 years down the line or 10 years down the line. So what's going to happen is, uh, some companies are working to, or some research groups are working at making analog systems. The good thing about analog is they don't need memory, or they don't have memory, and everything happens almost in one shot. Now the essence of that is they're looking to have processing at the location of the memory itself. So where your data is stored, it will be processed there, and then the output will be sent out from there only. So they're trying to make such kind of circuits in order to build better systems, build time and energy efficient systems. But this also has certain practical issues. Like analog systems are a lot prone to noise, and they are less reliable than the digital systems. So the research is going on, and let's hope we might, if this hits out, then we might have a lot of growth in this field. But let's just see what happens. And another thing is at the device level. So I'll show you one slide. This is the Intel. So there is something known as a beyond CMOS device, basically a beyond transistor device. You can Google it, you can read about it. So modern day transistors kind of look like, I hope this slide has that. Okay, they don't. So modern day transistors, the issue with modern day transistors is that we're trying to make them smaller and smaller each day. And they have a fundamental limit. The industry right now is at 3 or 2 nanometers of transistor gate length. We are trying to reduce it to 1 nanometer or even below. And things below 1 nanometer are basically 10 atoms or 15 atoms stacked together. And there we have a fundamental limit that we cannot do much with it, because we cannot shrink it further. We cannot, because where are you going to go below 10 atoms or something like that? So there is an inherent issue that a transistor is going to face in the future, because we might not be able to shrink it more. And the advantages that came with shrinking, like energy efficiency, will not be observed. And this is a big challenge for the society, because if our computing systems do not grow at the rate that we want them to, then research will not grow. Other technologies will not come into place as quickly as they do right now. And you can see where I'm going with it. It will be like a global challenge, and there are billions of dollars being spent to solve this problem itself. So there are certain devices which are known as beyond CMOS devices or beyond transistor devices. Like, people have started, and even these companies and research groups have started to look beyond the transistor. What they want now is, they're not looking for a size deficit, because size is not really an issue. We're already at the nanometer range. What they're trying to do is they're trying to use these new kinds of physics to create more energy efficient, more quicker devices. Does not matter if the device is, let's just say, 30 nanometers or 40 nanometers. It's still pretty small. But if it takes energy that is 10 times lower than a normal transistor, then why not use it, right, for such applications? So there are a lot of contenders that are there, even beyond this PPT, because this PPT only has some of them. And a lot of people, there's actually a lot of money involved if you can be the next guy to bring in a device that either can replace the transistor or that can be used with it for such kind of applications. And what essentially a lot of these guys offer is they are non-volatile devices. They have memory in them. So the caveat is that if these guys can store some information in them, then you can actually use certain kinds of circuits to do processing at their location itself, and then build such architectures and run whatever algorithms you have. And this will be very, very efficient if this becomes a possibility. Because here's the thing, uh, here in digital systems, you all know they take some cycles to fetch from the memory, then some cycles to process, then some cycle to interchange it here and there, and then store it back in the memory. What these kinds of systems are trying to offer is uh, a one-shot solution, or maybe not one shot, maybe 5-shot solution. Like in 5 cycles, everything will be done all around, not just in like one cycle. In 5 cycles, you can maybe train your whole neural network. That is what these guys kind of propose, and that is, I know that is the ideal goal, but and that will not be reached, I guess, because of a lot of challenges that are there. But the essential thing that lies here is that if you can build a device, and definitely we have the industry that can build the circuits out of it, then these problems will be solved in a very quick, in a very energy efficient way. And you probably can have like a whole neural network trained on your phone, and you won't even need internet for it to speak, for it to interact with you. And you can have like robotics field can take leaps and leaps of growth, because these are the things that has been restricting it from time to time. And somewhere or the other, maybe if something big happens at the device scale, there might be a Nobel Prize for people who discover this. Because if the people who discovered the transistor got a Nobel Prize, the people who improved the transistor into CMOS got a Nobel Prize, the people who improved memories got a Nobel Prize. And the way this thing will change everything, if a device is proposed or discovered, then the kind of impact it will have will be what the transistor has today, all these systems, everything. And it will open space for newer things, newer logic. So yeah, like I can just go on and on about this, but this is the essential brief of neuromorphic computing. So if any of you guys would like to explore this field, go out in this field, this field is actually broad. This is broader than artificial intelligence or machine learning, because this has elements of AI ML, and this has elements of circuit design, this has elements of computational neuroscience, this has elements of circuits and devices. Even physics people are working on these problems, because these kinds of problems now is not the time where specialized people can solve these kinds of problems. You need people from different places to come together. So if your interest kind of lies in these fields, and you kind of like what is happening here, then you can definitely explore it. And a lot of people have this notion that this is just for the computer science people or machine learning people. That is not the case. I personally am a device guy, I'm a circuits guy, and I have explored this field a lot, because this field requires innovation on all these aspects. And maybe as a professional career, if you want to go to the industry, there are companies working on such architectures. You can hit them up if you're interested in circuit design or algorithms and softwares. We have all the jobs we have for machine learning and AI people, data science people. And devices and circuits is still coming up, but you can maybe go for higher studies, maybe go for a PhD, or maybe go into a research lab that works on these kind of things. So the field has a very wide scope, and the amount this field has taken up in the past 10 years, because AI and ML has grown so much in the past 10, 15 years, that people initially didn't take this idea very seriously. But now this is like a trend that you see, like almost every other college you go, all around the world, every second or third college, they might have people, even circuits people, who might be getting into it, because this is what everyone is trying to solve these days. And it's not as easy as it sounds to solve. and it'll take its fair share of years. But definitely, with all these companies funding it, with all these new kind of solutions, with research going all around the world, we hope to see an improvement in these devices. So yeah, I mean, I aim to keep it short, and I hope I have kept it short, because I know a lot of you will have like this would be your dinner time and you won't want to miss it. So I'll be taking questions for the next maybe 10-15 minutes, if you have so. And if you're hesitant to ask anything, or if you need general, if you want to interact, if you also need some guidance, if you want to know about this field more, or in general, if you want to know about the industry or higher studies, or maybe hardware related things, you can just contact me on WhatsApp, drop me a message, drop me a mail, contact me on Instagram or on LinkedIn as well with this name. And that should be it, I guess. I hope I have given you a bird's eye view of what this field really looks like, how things are happening, state of the art in the industry and all around the world in research labs, and maybe where you can get your fair share of pie, whichever piques your interest. So thank you so much. If you guys have any questions, feel free to ask me. Uh, Send them down in the chat. You can maybe unmute your mic, or maybe ask either ways you want. I'll be here. Or you can contact me directly if you have some questions. So will you guys be moderating it, or should I just read from the chat?
Thank you so much, sir. And I hope the talk session was very informative to all. So let's move to the Q&A session. So if you have any doubts, you may drop it in the comment section. So we have one question in the chat box.
Okay. Hi.
Do you want me to read it?
Yeah. No problem. I can read it. Hi, Deepu. So the question is this technology help us to make humanoid robots with a brain that can think exactly like the human brain? Now, that is exactly what the aim is. So in the previous slide, I showed you different areas that actually, that are needed to actually get to this goal of making a processor that works exactly like a human brain. That is the end goal. But in there is one field that is a computational neuroscience. So what those guys do is they put probes all around your brain. These are like biology people or biomedical people. They put electrodes on your brain and they measure different kind of uh, outputs in the EM waves that the brain uh, emits. And what these guys do is these kind of reading them. So for example, if I plug a lot of probes around your head and I show you an apple, I will see how that pattern behaves, that output pattern of EM waves. And then maybe I'll put a banana and then I'll see how that pattern behaves. Now I can try to make a system. Hence, this is the neuroscience part of it. Now comes the computational part of it. I can try to make a software, or I can try to make an algorithm that takes these kinds of input, these kinds of waves as input, and maybe you can create a helmet. When you put it on and someone puts an apple in front of you, it can send an output that this is an apple. So this is the end goal. But to achieve this, we need a lot of things. And human brain is something that we don't understand a lot about. Like we probably understand 5 or 10% of how it works. Either way, using that 5 or 10% and using some more of human innovation, we have been able to bring in phones and such systems that we can. And then we're going to run calculus. Such systems, we can make such systems that can recognize voice, can recognize images, and they're doing pretty well. But so imagine if with 5 to 10% of human brain working that we know, we can understand, we can create so many applications. Imagine if we go around to 9%, 90% or 100%, we're able to mimic the human brain. So it needs all those fields to go in a coordinated pattern. Like people from biology, people from biomedical engineering should need to figure out how the brain works, how the systems work. Then some algorithm guy needs to figure out how the algorithm will look like. Then we need these devices guys to build these devices which can be used in a very efficient way. And then we need architecture people or circuit design people to make circuits out of those, to make hardware where those algorithms can run. So definitely it's a long way, but the way this thing has taken a pace, I'm pretty sure we'll get maybe a full-blown neuromorphic processor in 5 years of time, and if everything goes well, a neuromorphic processor with a new kind of device. So you can expect like 10 to 100 folds of improvement in today's technology, maybe in 5 years of time. And yeah, so you can make a humanoid ideally, theoretically, yes, with the human brain, but practically, we'll see how it happens. But yeah, there is a possibility, and that is the end goal, to be honest. I hope that answers your question. Okay, Anthony has a question. What is the future of neuromorphic computing and how it will change the future? So here's the thing. Think about how artificial intelligence and machine learning is changing things, and how they can bring in new technologies like robotics, new kind of automation, space exploration. They can increase the basic research that is happening by many folds. IoT is one application. You can enlist all such applications of AI and machine learning. And neuromorphic computing aims to tackle this problem that AI and machine learning is facing while you run it on the current computing system, on the current hardware that is there. So if you can build such kinds of systems, all the things that AI and ML you can think about, and maybe even a bit more, that can be changed because of neuromorphic computing. And some examples I've already told you, like IoT, Internet of Things, all these image sensing. Your phone might behave maybe in 10 years of time what a Google cloud server right now, the processing capability your phone might have exactly if this technology comes in. So like at the current pace, how the technology is going, neuromorphic computing, if these architectures, these things are included, they might, increase the growth by tenfold. So you might see things that you never expected to come in 20, 30 years, coming in like 5, 10 years. That is the potential that this thing has. It's comparable to AI and ML that we dream about. Okay. Any other question? Anyone wants to know anything else? Okay, Arnold has a question. Okay, Arnold, so I'll tell you what current systems are. Current systems are basically digital systems, as I mentioned. They have different memory and different processing. What happens at the brain level is, I'll give you a brief description. In the brain, there are different these biological systems. So you have one thing which is known as a synapse. Okay, and you have one thing which is known as a neuron. So consider neuron as a circle that you have, and it has a lot of synapses that are connected. You can, for now, it's not accurate, but for now, consider synapses as nerves coming on to one point. Okay, so different nerves come on different points. Now, the way it behaves is, there are trillions of neurons in your brain. Consider them as certain units which can, and those neurons are interconnected with a lot of maybe veins or with a lot of arteries that are there. If I put an apple in front of you and I tell you this is an apple, so because of the inputs from the eyes and the ears, your brain will try to link that shape and that color to an apple. And what essentially will happen is, there will, because of these sensory inputs through those nerves coming onto those neurons, a pattern will be formed, a rough pattern will be formed. So these synapses act like have a certain weight to them. So if they're coming from the eye and there is a shape, so they will come in a particular pattern, and they will lead to certain of these neurons getting activated. And if I show you a banana and I tell you it's a banana, different sets of neurons will get activated because of these synaptic signals, right? So this is what is happening in your brain that we know about. There is a lot that we don't know about, but what we know about is this is what is happening. And this is very continuous in time. This is analog in a way. This is not digital. There's no discretized thing. There's no memory. There's nothing like that. This is very analog. And to make analog systems, the issue is that, there's a lot of noise around. There are a lot of EM waves that are traveling. There are a lot of, if you study circuits, there is always some kinds of noise, white noise, different noises due to different reasons. And hence they are a bit less reliable in the certain technology that we have. So that somewhat limits us to get exact, because the brain kind of works in a complete analog fashion. So current technology, digital technology, is very limited in terms of how it can be faster than the human brain, agreed, but it is not as energy efficient as the human brain, because your human brain probably uses a small 9-volt battery's energy in probably a month or a year. That is how energy efficient it is. And it is not as robust as the human brain. But the end goal is to make it as robust as the human brain. That is why we're looking for analog systems as well, to exactly mimic that. And we're trying to, even if you study AI and machine learning, the certain architectures that are there, that there are certain weights that you store. And every input is connected to every output in all possible ways. And all those connections have weights. So that is somewhat we've taken from the brain. That, okay, if the input comes, it gets multiplied through those weights, which are known as the synapses. And then depending on those weights and depending on the final addition, some outputs get activated. So if it's an apple, the output corresponding to apple will get eliminated. So that is how the brain works. That is what we know how the brain works in a very rough way. And that is how we try to mimic them in algorithms and then on a circuit. But yeah, it's still pretty far. We need to address a lot big blockers in the technology that we have today. But let's just see what happens in the next few years. But yeah, I hope that answers your question. Okay, Jilna has a question. Okay, this is a particularly interesting one. How is neuromorphic computing different from other technologies like quantum computation or high performance computing? Okay, Jilna, high performance computing is actually what happens in supercomputers or maybe cloud servers around the world. What those guys do is they take a lot of memory, very fast memory, and a lot of processing power, and they just store it in one place. And what they do is, okay, if one task is taking a long time, what they do is they distribute that task into a lot of pieces and run it parallelly so that it happens quickly. But the compensation that is there is that requires a lot of energy. That is why most of these servers or HPC systems you'll see are in very well temperature controlled places. There are ACs and freezers involved because they generate so much amount of heat. Now, to just think about building such systems in your phone is impossible because your phone will simply melt. So HPC is at that stage, and HPC, this kind of technology aims at bringing all that kind of computational power right to the edge, right to your phone or maybe your laptop. Or even if you cannot bring it to your laptop, you can make certain hardware that is so efficient at your HPC that you don't need to control the temperature maybe, or maybe you can still get your outputs in a very quick way. So that is about HPC. Now, also HPC is a generalized word. Right now it uses digital systems, but neuromorphic computing is open. It can range from software to digital analog circuits to devices. So it's about bringing these new kinds of devices, new kinds of circuits to address these AI ML problems. And why not, if you can implement these systems, we can use them in our HPC server as well. Now, quantum computation is a whole different ballgame. All right, I'll just take 2 more minutes. Quantum computation essentially uses something that is not your digital system. It uses something known as a qubit. It uses this new physics. It uses a new kind of physics, and this uses a qubit that can take any state between 0 to 1. But the thing in quantum computation is that the end state is always either 0 or either 1. But since in between they can revolve in either state between 0 and 1, you can use it for processing in a much parallel way. And the problem with quantum computation right now is we cannot make practical systems out of them. The systems that you see on the internet are cooled down to 100 Kelvin, that is like minus 200 degrees Celsius. And those are like big systems with temperature control, laser cooling. And so quantum computation might still have 20 years to come to a technology like a laptop or your phone. Secondly, for quantum computation, you need different kind of algorithms. Your standard AI/ML algorithms won't work. And yes, there is a very new field in neuromorphic computing that aims to make AI algorithms run on quantum computers. And yes, that quantum AI or quantum ML that people call QML is also a part of neuromorphic computing. It's just that it's a very nascent field. It's been around for like 3-4 years only. So that will take a lot of time. So neuromorphic computing kind of envelops everything. Its main goal is we want to run these AI ML algorithms very effectively and efficiently on any hardware. So we want to make hardware for that. That can be a quantum computation based hardware. That can be an analog hardware. That can be a digital hardware. So it's kind of like an overlapping umbrella. I hope that roughly answers your question. Okay. So anyone else have any question or anything they'd like to discuss about? I guess I can wait for a minute more, and if not, then you can wind up and have dinner. Okay, Shilpa has a question. Are there any working on neuromorphic models currently? So this is a very broad question. Like, do you want me to tell any specific industry, or do you want me to tell any specific field? So the thing is that companies I've already showed you, Google, Intel, IBM, Samsung, Nvidia, everyone is trying to incorporate these neural engines in their processors that can, in a way, maybe if not solve these AI/ML algorithms completely, maybe they can offer a bit of, relaxation in terms of time and energy that is used. So those companies are actually the main HQ, main R&D centers are actually working on such models and trying to incorporate them. But they're mostly working on digital systems. There are very few companies, and they are in startup stages, but there is a company known as Mythic, MYTHIC. You can Google it. It is making analog or digital analog mixed processors based on specifically for AI/ML, though that is specifically for neuromorphic computing. And a lot of these companies like Intel and Samsung are funneling in money in a lot of universities and research labs to discover these new kind of devices that I just showed you a couple of minutes back. So they're funneling money, and those research labs are working on making these new kind of devices, which can be used for such neuromorphic computing applications. So many people believe that ideally the future is going to look like this. You'll have your normal processing and normal applications or your digital systems, transistors, everything. And on top of that, you'll have certain dedicated hardware, be it digital, be it analog, be it some new physics device that is there. You'll have that stacked on top of it, and that will do those kinds of tasks, and it'll relay information to your conventional digital hardware. So it's probably going to be a mixed one. There are 3-4 devices that are in this race, and some people project that maybe you might in the future you might have a system that utilizes all those 3-4 devices for different applications. Like some devices better at storing. Cool. We might use it for memory applications where processing happens there itself. Some device that is more energy efficient than a transistor. Cool. We might use it in some applications that takes a lot of energy. For example, these machine learning training that happens. So, different devices have their different abilities. So let's see how the future goes. It's rare that we'll get a device that might tick all the boxes that are there all the requirements. If we get it, then there's a Nobel Prize, or there's a lot of prizes out there for that person or that group. But if it does not, then the future will look mixed, where you have transistors and other devices, different kinds of circuits for different kinds of applications. And yes, you can search for, if you want to go into research, you can search for different universities in India, outside India, where they are working on neuromorphic computing, different aspects of it, and industries also as well. Okay.
Okay, thank you all. I hope all the doubts are clarified. Now I invite Govind G. Krishnan, Chair IEEE RAS SJCET, to deliver vote of thanks.
Hello, are you audio okay?
Yes, Chair.
Good evening, everyone. First of all, I would like to thank you all for signing in today for this session. I thank you, Mr. Utkarsh Singh, for sparing some time out of your busy schedule and delivering such a wonderful and enlightening session. It was very informative and enlightening, and we truly appreciate your efforts. As a token of our appreciation, we would like to present you this virtual memento. Hope you like it.
Yeah, it's very well made. Thanks a lot. Thanks a lot to IEEE SJCET, and specifically to Robotics and Automation Society. Thank you, Raina. Thanks a lot, Gokul, for coordinating with me in the initial stages. And thank you, Jilna, for a very smooth coordination till the end. And thank you, everyone, for being here. I hope it was worth your time. And I hope if you have any doubts, feel free to reach me in the, via LinkedIn, Instagram, WhatsApp, any social media that you might find me there. Yeah. Thanks a lot.
I would also like to thank Dr. Arun P., Branch Counselor of IEEE SJCET, and all other EXCO members for supporting us in conducting this session. We wish you all the best in your future endeavors. Once again, I thank you all for signing in today. And guys, do not forget to fill in the feedback form. It's in the chat box. Links in the chat box.
Thank you so much. Thank you so much, sir, for sharing time with us, and also to the wonderful audience. Thank you for being a part of today's session on the behalf of IEEE RAS chapter. Once again, thank you all. Thank you so much. The feedback form is provided in the chat box. Please do fill it. Thank you.
Thank you so much, everyone. Bye-bye. Take care.